This is lecture 4 in BBSP 710. Today we're going to discuss blocking and a brief introduction to sampling, the last elements of experimental design that we're going to discuss in this class. So recall that when designing an experiment, you want the treatments and control groups to be as similar to one another as possible, other than the treatment itself. If there's some systematic differences between the two groups that are unrelated to the treatment, you can find spurious associations due to confounding. And the best way to ensure that the two groups are comparable is randomization. If you just randomly assign observations to the treatment group and the control group, then generally speaking there should be no differences. The probability of a systematic difference occurring due to chance is very low. And complete randomization works great when you have a large sample size, but it can be problematic when your study is smaller, which will frequently occur in bench science. Oftentimes, if you have, say, only 6 in your treatment group and 6 in your control group, if you just assign randomly, you could end up with, like, say, for example, 6 men in the treatment group and 6 women in the control group, which is something that you want to avoid. Oh, in cases like this, if you know a potential confounder exists, like gender, then you can use blocking to try to avoid that problem. And I'll illustrate this with an example. This was an example on turkey growth. Methionine is a sulfur amino acid that's added to the diets of turkeys to enhance their growth, and we want to compare 3 types of methionine that we'll call T1, T2, and T3. And we'll do this by giving each of the 3 types of methionine to a group of turkeys over a 3-week period, and we'll see how much they weigh at the end. A confounding variable in this particular experiment is the location of the cage, and we'll just for the sake of this example, we're going to say that the cages are in a 4x3 grid where you have 3 cages on the floor, 3 cages on the next row, etc., all stacked one on top of another. The cages near the ceiling are warmer than the ones near the floor, and a turkey's diet can depend on the temperature. And if all the turkeys that were given the T1 supplement were on the floor, then the effect of treatment could be confounded with the effect of temperature, and we wouldn't know if T1 caused the turkeys to grow more, or if it was just because the turkeys ate less because they were on the bottom floor. So to avoid this, you use a technique known as blocking. Here's a diagram of blocking, which is basically that you first partition your data set into more homogeneous subgroups, then you do randomization within each subgroup, and that ensures that the two groups are relatively comparable to one another. And so you try to find suitable blocks of experimental units that are similar to one another, and then you randomly assign the treatment or treatments within each block. And you want to try to make the blocks as homogeneous as possible. You want the extraneous variation, the variation unrelated to the treatment, to occur between blocks rather than within blocks. There's several advantages of blocking. First of all, it avoids the risk of confounding. In the turkey example, it avoids potential confounding due to where the cage is located. You can also show statistically that your sampling variance is actually reduced when you do blocking correctly. But this only works if the blocks are homogeneous. If you do a poor job of blocking, then the variance can actually be increased rather than decreased. So, as I said before, in the turkey example, you can let each row of cages be a block, and since there's 3 turkeys on each row, on each row of cages, at a given height, you give one turkey T1, one turkey T2, and one turkey T3, and this will control for the effect of temperature and will lead to more accurate results. Another example that might be more relevant in the bench science world is an experiment they wanted to see how social activity develops or affects the development of brains of young rats. So young rats are placed in one of three environments for 80 days. In the standard environment, you put the rat in a standard cage with one companion. In the enriched environment, you give them several companions in a large cage full of toys. And in the impoverished environment, the rat's housed alone, and you want to compare the brains of the rats in these three groups. So after 80 days, you're going to collect anatomical measurements on the rat's brains, and so the question is, how can we design this experiment to minimize potential sources of confounding? So say you have 30 rats for this experiment, and first thing you do is try to control for obvious confounding variables like the gender of the rat. Male rats tend to be larger, and so you want them all to be male of exactly the same age and coming from the same strain. But even within the strain, there are certain variations, so you can use blocking to take advantage of the fact that rats within the same litter are likely to be similar. Say there you have 10 different litters, you select three rats from each litter. Among those three rats, you assign one to T1, one to T2, and one to T3. That means there's one rat from each litter in each of the three groups, reducing the potential of confounding due to litters. Another example is you can also do blocking within subject. Say you have two lotions for treating acne, you have 20 participants in your study, you want to see if one lotion is more effective than the other for treating acne, and what's the most efficient way to do this to get as much useful information as possible? Well, the naive solution would be to assign half of the patients to receive treatment A and the other half to receive treatment B. But this is suboptimal for several reasons. I mean, obviously it reduces your sample size, but in addition to that, there's quite a bit of variability between individuals with respect to the amount of acne that a person has. You could very easily end up with confounding if you just got unlucky and a bunch of people with lots of acne ended up receiving lotion A. So a better approach is to do within subject blocking where you take all 20 subjects and you tell them to use lotion A on one half of their face and lotion B on the other half of their face. The side of the face that receives lotion A is chosen randomly, and you have coded labels so that neither the patient nor the physician knows which lotion was applied to which half of the face. And this accounts for the individual to individual variation, and as an added bonus, it increases your sample size and gives you better power. Or another bench science example that we discussed briefly earlier, let's say you have a microarray experiment. You want to compare two different treatments that we call T1 and T2 on two different cell lines that we call C1 and C2. So, and we already know that C1 and C2 have different gene expression profiles, and as I described in the earlier lecture, dye bias is another potential source of confounding. Sometimes samples labeled with a red dye or with a green dye will be expressed at higher levels simply due to mechanical variation. The best design here is that you create four blocks. The two meta blocks we can say of C1 and C2, and then within C1 and C2 you assign half of them to get the red dye and half to get the green dye, and likewise for C2. Then within these 4 blocks, you assign half of the block to get T1 and half to get T2. So when all said and done, you've partitioned the data into 8 different pieces. This allows you to see the effect of the treatment on gene expression while controlling for both cell line bias and dye bias. Well, things to remember about blocking is that it will reduce bias and variance, but blocks must be as homogeneous as possible, and it's not a substitute for randomization. You still have to randomize within blocks to control for unknown confounding variables. As one textbook that I used to use put it, block what you can and randomize what you cannot control. So now on to sampling. That Generally speaking, you can't study an entire population of interest, so you have to take a sample of the population. And when you take a sample of a population, you want to take the best sample possible in order to avoid introducing bias into our studies. So some terminology is population is the group of individuals that you'd like to know something about, which is typically very broad. Say you want to know something about women between the ages of 20 and 45 in the United States. It's going to be very difficult to obtain information on that full population. So let's say our target population is women in this age range who live near Chapel Hill, North Carolina, because those are the ones we can realistically recruit for our study without spending tons of money. And within the target population, there's a smaller set known as the survey population, which are subjects in the target population that we may potentially obtain information from. If, for example, you recruited study participants by random digit dialing a database of phone numbers, then you would miss anyone who doesn't have a phone or anyone whose name isn't in the database. In many cases, this is unavoidable, but if there are systematic differences between those who are in the database and those who are not, that could result in bias. I'll give a couple examples of this here in a minute. When you define a target population, you should define it very specifically. Say what you're collecting, whether it's people or if you're comparing medical clinics, then it would be clinics. If you're comparing different cell lines, whatever the case may be, a place and a time. So, for example, if you're doing a study on menstrual pain, I did a study on this a while ago, which is why it popped into mind. Say that you were recruiting women between the ages of 20 and 45 who live in Chapel Hill between 2008 and 2010 when the study was performed, for example. And as I briefly noted earlier, there may be differences between a target population and the survey population, and this can occur because of 2 reasons. One is non-response, when you have a way to measure a particular experimental unit but you don't obtain the measurement. For example, you give the person a survey about menstrual pain but they refuse to fill it out. Or undercoverage is when the researcher simply doesn't have the ability to measure this experimental unit, that a person doesn't have a telephone, so we never call them to try to bring them in for the study. An example of this was a childhood obesity survey that was conducted in Australia. They were trying to determine the relationship between childhood obesity and the quality of life among elementary school children. So the population of interest was elementary school children in Australia, which is much too large to sample from without extreme amounts of money. So they set up a target population with children in grades 3 to 6 in Victoria of Australia in the fall of 2000 who had previously participated in the 1997 study. You just have to hope this particular target population is fairly representative of the population as a whole. And the survey population is the members of the target population from whom we can collect data. For example, it doesn't include people who moved away or who refused to fill out the survey. At any rate, once you've defined these populations, then you can collect a sample. A sample is when you just choose part of the population and draw data from that population. It's typically a subset of your survey population. For example, you could select 130 employees out of 2,500 to fill out a questionnaire on workplace safety, or you could take 2 spoonfuls of chili out of a pot to see if the chili is spicy enough. And the best type of sampling is what's called probability sampling or random sampling, which every member of the population has a known non-zero probability of selection. Members of the population are selected by chance. Normally, in most simple situations, you'll just give an equal probability to everyone, so the people who are selected are, so everyone has an equal chance of being selected. If you're doing like a large scale telephone survey on who people are going to vote for president, for example, then you may do some sort of weighted sampling where you want to make sure that you don't interview too many or too few African Americans, for instance, so you increase or decrease the probability of selecting African Americans to make sure you get a sample that's representative of the population, but that's beyond the scope of this course. I won't describe that in any detail. The important take-home message is that you should use probability sampling, that is, select your sample randomly. Examples of non-probability samples are anecdotal evidence, which would be that you selected some data points just because they were unusual or interesting. Some other possibilities are selection by the data collector. The data collector selects units by some method other than random selection, whoever they can contact most conveniently, or whatever the case may be. Or other possibilities, selection by expert, that a knowledgeable investigator decides the particular examples that you chose are quote-unquote typical. A voluntary response sample, subjects choose whether or not they want to be part of the study. All of these methods can give you wildly misleading results. I'm going to briefly describe a couple disastrous examples of this. In 1936, the magazine Literary Digest performed what is to this day one of the largest presidential election surveys ever conducted. They surveyed 2.4 million people, and they predicted that Alf Landon would defeat FDR in a landslide. If you remember your U.S. history, you know that they were spectacularly wrong about that one. In this case, the issue was that they had a survey population that was not representative of the overall population, and that they only surveyed their own subscribers and people who had cars and telephones, because these were the people that they could contact easily. These people were much wealthier than the overall population. Cars and telephones were still luxury items at the time, particularly in the middle of the Great Depression, so you ended up with the sample that was biased grossly in favor of Landon. You would think that people would have gotten smarter after that, but as you remember US history about 20 years later, there was another example where the pollsters got it spectacularly wrong. I guess it was closer to 10 years later, but anyway. If you've ever seen this famous picture of Harry Truman holding up a copy of the Chicago Tribune saying that he lost to Charles Dewey in the election. There's various reasons why the polls were so horrendously wrong in that particular election, but one of the big reasons was that in 1948, when this occurred, most pollsters used what was called quota sampling, which was a primitive idea form of the idea I just described earlier, that it said you need to have a certain number of women in your sample, a certain number of poor people, a certain number of African Americans, etc., etc. But as long as they met their quota, they could interview anyone they wanted. So once again, interviewers ended up contacting wealthier people because they tended to be easier to contact. They would have phones or whatever the case may be. So you ended up with pro-Republican bias in the sample. In fact, if you look at a lot of presidential election surveys from that day and age, there was consistent Republican bias in the surveys because they tended to over-survey wealthier people, or at least that seems like the most plausible explanation. So, these all illustrates why non-random samples should be avoided, that they may be cheap and convenient, but they're often very highly biased. And if a sample's biased, a large sample size will not help you. The Literary Digest poll is one of the largest samples in history, but it still gave wildly misleading results. As an aside, if you ever watch on TV when they do like web polls of who are you going to vote for president, who should win American Idol, whatever the case may be. That's why they always put this disclaimer, these results are not scientific, because oftentimes, even if they get a large sample size, these polls are wildly unreliable, because the people who participate in these polls tend to be people who have strong feelings about the subject, which is not representative of the overall population. Oh, moral of the story, use probability sampling whenever possible. That is, just sample randomly from your survey population, giving equal probability or approximately equal probability to each person. And the benefits of probability sampling is that it eliminates sampling bias and it controls sampling variability in that, as we'll discuss later in this course, you can estimate the amount of sampling variability. You can never eliminate it entirely without surveying the entire population. The one drawback is that it tends to be more expensive than non-probability sampling, but in the vast majority of cases, that's a price that you're willing to take, simply because if you use non-probability sampling, as I illustrated here, you can get wildly inaccurate results. And any sample, there's going to be a certain amount of variability that if you do a presidential election survey, you could get extraordinarily unlucky and interview 300 people who all intended to vote for Mitt Romney, even though the truth is that Barack Obama was going to win the election. That's extraordinarily unlikely, but it could theoretically happen. And the fact that each sample is slightly different and may not be perfectly representative of the population as a whole is what we call sampling variability. You can always reduce it by taking a larger sample, and when you have a probability, sorry about that, when you have a probability sample, you can measure the amount of variability and calculate the sample size that you need to get an acceptable level of variability. All of this is stuff that we'll discuss in more detail later in this course. So, there's two types of error that can occur when you're sampling. Sampling error is the error due to the fact that you're not surveying the entire population. You might get slightly more Romney voters or slightly more Obama voters than you would get in the overall population. And non-sampling error is when other types of error occurs, logistical measurement errors, you design your experiment poorly, whatever the case may be. And in general, pro probability sampling cannot overcome non-sampling errors. That is, if you measure the data incorrectly, if you enter it into the computer incorrectly, if the way you phrased your question was confusing or misleading, if people don't answer your question, don't answer your survey, or leave part of the questionnaire blank. All of these things can result in non-sampling error that probability sampling won't correct. Some types of error would be measurement error when your equipment doesn't work correctly, you don't train your interviewers enough so they record the wrong thing. Processing error would be incorrect computer programming, or you entered it into the computer incorrectly, something like that. Physical problems with the data. Those of you who are old enough to remember the 2000 presidential election may have heard about hanging chads. Makes me feel really old to know that particular example becomes more and more obscure to people who weren't old enough to pay attention to presidential politics when that happened. But anyway, another thing that can cause problems in survey research especially is the wording of the question, that depending on how you word a question you can get very different answers that say like abortion versus termination of pregnancy, welfare versus aid to the poor, because sometimes when people hear words like abortion or welfare they give an emotional response or a preconceived response that isn't the same as what they actually believe. Sometimes people lie about certain subjects like illegal drug use. Sometimes if a question is worded poorly, that can cause people to get confused. My favorite example of this is from an OBGYN that I worked with, and she was on call in the ER one day, and a woman came into the ER with some abdominal problems. My friend asked her, "Are you sexually active?" And the woman said no. Oh, apparently for the procedure she was running, just as a matter of protocol, she does a pregnancy test, and the pregnancy test came out positive, and my friend was completely freaking out. It's like, how am I going to break this to this poor woman that somehow she's pregnant? So she told the woman she's pregnant. The woman didn't seem phased off. It's like, oh, okay, that's good to know. And so my friend was just like, whoa, wait, what? I thought you just said that you're sexually active. How are you pregnant if you're not sexually active? And the woman was like, oh, I thought sexually active meant that, like, you're doing it all the time, like 3 or 4 times per day or something like that. I mean, if you're just asking if I have sex, yeah, I have sex. So, anyway, the point is, if people don't understand what the question's asking, you can get unreliable results. Another source of error, as I said, non-response or undercoverage. If people who refuse to participate in the survey are not representative of the population as a whole, that can get bias. If you recall the Salk vaccine example, those who refused to participate in the vaccine trial tended to be poorer and had lower risk of polio. The non-response in that study potentially biased the results. Undercoverage, if there's no way to contact certain individuals. The Literary Digest poll is a good example of that, that they only contacted people who had cars and phones. The people who they couldn't or wouldn't contact were very different from the set of people they did contact, resulted in misleading results. So the things to remember is that when you can't examine an entire population, you perform you do a sample of the population. Probability samples or random samples are always preferable to non-random samples, and you want to be careful to avoid possible sources of error when you do your sampling.